Today we continue our discussion on advanced synthesis problem. In the last lecture, we have seen how a multi-stage procedure can be applied for the design of a 6-link mechanism to be used as a forklifter consisting only of R pairs. As a second example, today we discuss a 6-link rail-less garage door mechanism. This figure shows the sketch of the proposed 6-link mechanism to be used as a rail-less garage door. This member EC represents the door board. The fixed hinges or fixed pivots of this mechanism is at O2 and O4, which are mounted on the side wall of the garage. This is the floor of the garage and this is the roof. So this is fixed link 1, O2AC, this is link number 2, AB is link number 3, O4B is link number 4, and BD is link number 5, and the door board EC is link number 6. So you see we have total number of links N equal to 6. We have 1, 2, 3, 4, 5 revolute pairs which are connecting only 2 links. So J1 simple hinges is 5. And at this revolute pair B, 3 links, namely 3, 4 and 5 are connected. So we have a second order hinge, J2 is 1. So the degrees of freedom of this mechanism using our known formula is 3, F equal to 3 into n minus 1 minus 2 J1 plus 2 J2. If we substitute these values, we get 3 into 5, 15 minus 2 into 5 plus 2, 7, 14 is equal to 1. So we have a single degree freedom mechanism. Now the question could have been asked, why 6-link mechanism is used? We could have used the door board as the coupler of a 4-link mechanism. But it was found that using only a 4-link mechanism, it was not possible to have the desired motion of this door board. What is desired? That the door board, when the garage is open, should remain parallel to the roof, that is horizontal, and in the closed position, when this linkage is moved, the door board becomes vertical to close the garage. From this horizontal to vertical transition, the door board should not take too much space inside the garage because the car is kept here and that will interfere with the car. This rest of the mechanism is mounted on the side wall. Now we shall show the model of such a mechanism to demonstrate the desired motion that is required. Let us now study the model of this proposed 6-link mechanism. This is the door board which is horizontal parallel to the roof of the garage when the garage is open. And by driving this mechanism, we can close the garage and the door board becomes vertical. If we see the movement of this garage door from this open to the closed position, what we should note that the garage door board is not interfering with the car that is kept inside, and the car is quite a high car. Thus, the motion of this garage door board is almost horizontal and then suddenly falls to the vertical position. And such a movement is not possible by using a simple 4-link mechanism with this as the coupler, the door board as the coupler. So we go for this 6-link mechanism. And now we shall give the details of the design of this 6-link mechanism and determine all the kinematic dimensions by applying the multi-stage synthesis procedure that we have learnt earlier. So this sketch we show that O2 and O4 are the location of the two fixed hinges on the side wall. The locations of these two hinges we choose conveniently wherever it is possible. C1E1 is the door board when the garage door is closed and it is almost vertical. C3E3 is the door board when the garage is open and this C3E3 is almost horizontal. We consider an intermediate position C2E2. The length of the door board is also taken as the height of the garage to be closed. It is also specified that the fourth link, which is connected to O4 up to the point B where there was a second order hinge, 3 links are connected, that point we call B. This O4B is the link 4, and it is also said that the rotation of this fourth link theta 4 1 2 from configuration 1 to configuration 2 is 12 degree clockwise. Similarly, theta 4 2 3 is also prescribed that it should be 26 degree clockwise. Our task is to determine the rest of the linkage, that is the location of the second order hinge at B and also the hinge at D on this door board CE. And we shall determine the linkage at the third configuration. That means we shall determine where is B3 and D3. Now let me show you the complete design specification for this particular linkage. The scale of the drawing is shown here. This is 10 centimeter. The complete design specification for this particular mechanism is as follows. We have given 3 configurations of link 2 and the door board. The door board, that is that link CE or link number 6, is specified for closed position, which we call position 1, open, which is called position 3, and intermediate, when is that we call position 2, configuration 2. It is desired that theta 4 1 2 is 12 degree clockwise and theta 4 2 3 is 26 degree clockwise. Our task is to obtain the complete linkage corresponding to the open configuration when the door board is parallel to the roof or horizontal. All other kinematic dimensions and the locations of the hinge point will be determined, has to be determined for this particular 3 configurations. So as I said earlier, O2 and O4 have been chosen arbitrarily. 3 positions of the door, C1E1 closed, C2E2 intermediate, and C3E3 open, these 3 configurations are given. And we would like to determine the rest of the linkage corresponding to this third or the open configuration. We achieve this design in 2 stages. First, we try to design the 4-link mechanism, 4-link part of this mechanism, namely O2A, B04. To obtain this 4-link mechanism, we conveniently choose the location of A, the hinge on this link 2. A1 is chosen arbitrarily. So we can immediately determine where A2 and where is A3, because these distances O4A does not change. In the first configuration it is here, because C2 is given, so O2 C2, this is the link, this distance remains same, so I can determine A2, and O2 C3, this distance remains same, so A2 comes to A3. So I know the 3 positions of this revolute pair at A, namely A1, A2, A3. Since we have to obtain the position of the hinge B at the third configuration, that is B3, we hold the link 4 fixed at its third configuration and make a kinematic inversion and determine the inverted positions of A1 and A2. A3 is nothing but A3, 3, because we are holding the link 4, that is O4B, fixed at its third configuration. This is A2. We have to determine what is A23. It is known that theta 423 is 26 degree clockwise, which means theta 432 is 26 degree counterclockwise. To determine the inverted position of 2, what we have to do? We have to rotate O4A2 through minus theta 432. Minus theta 432 is nothing but 26 degree clockwise. This is O4A2 and we rotate this through 26 degree. So O4A2 is this line and we rotate it through 26 degree. This angle, this rotation is 26 degree, because minus theta 432 is 26 degree, and this point I mark as A2 inverted on the third position, A23. Now A1 is here. Where is A13? Now theta 431 is equal to 26 degree plus 12 degree, that is 38 degree in the counterclockwise direction, because theta 413 is 38 degree clockwise direction. So to get to the point A13, I have to rotate O4A1 through 38 degree by minus theta 431, which is again 38 degree clockwise. So this is the line O4A1, and I rotate this about O4 through 38 degree in the clockwise direction. This rotation is 38 degree, and this point I call A13, because it is inverted on the third position of O4B, that is, and the rigid link AB is of constant length. So the circle, center of the circle passing through these three inverted positions, namely A3, which is A33, A23, which is here, and A13. So we determine the center of the circle passing through these 3 points in the usual manner. We draw the perpendicular bisector of these 2 lines, namely A23 and A13, and A33 and A23, that is this line. The perpendicular bisector of these 2 lines we can draw simply geometrically. This is the perpendicular bisector of A23, A13, and This is the perpendicular bisector of A33, that is A3, and A23. These two lines meet here, which will locate B3. This is where that compound hinge, second order hinge, is located at the third configuration. So to complete the 4-bar linkage, I have to join O4 B3 and A3 B3. O2, A3, B3, O4, that is the 4-bar part of this 6-link mechanism. Now we have to obtain D3, that is the hinge which is located on the door board. Because we are holding it in the third position fixed, so I have to find out what are the inverted position of B. To do that, first we note that where is B2 and B1? Because the link O4B is a fixed length, the point B moves on this circle with O4 as center and B as radius. And the rotation of the fourth link, this O4B, from second to third position is 26 degree clockwise. So from third to second, it will be 26 degree counterclockwise. So I draw a line at 26 degree from O4 B3. This rotation is 26 degree in the counterclockwise direction, and B lies on this circle, so I can locate B2, and if I draw another line at 12 degree, I get B1, because from position 1 to 2 it is 12 degree clockwise, so from position 2 to position 1 it is 12 degree counterclockwise. So I draw a line this angle is 12 degree and we get the position B1. This is B1. So we have located that compound hinge corresponding to the 3 configurations 1, 2 and 3 at B1, B2, B3. To locate the hinge on the door board D, I have to hold the door board fixed, because BD length is a constant length. So if we hold link 6, that is the door board fixed, then B goes on a circle with D as center. So we make a kinematic inversion holding the door board always fixed at its third position. To obtain the inverted position of B2 and B1, we use our procedure of kinematic inversion and use a tracing paper. We use a tracing paper and mark the relative position of the door board. Door board is completely specified by 2 hinge points on it, namely C2 and E2, and B2 is here. So we have marked, as we see here, 3 points, namely C2, E2 and B2 on this tracing paper. If the door board is held fixed in its third configuration, then C2 is made to coincide with C3 and E2 is made to coincide with E2, and wherever B2 goes, this point I mark on my drawing sheet, which is B2 inverted on the third position. B3 is nothing but this is same as B3 inverted on the third position. Only thing remaining is to obtain the inverted position of B1, which is here. This is the location of B1. So again we use tracing paper, mark C1, E1 and B1. This is C1, this is E1 and this is B1. So I now make a kinematic inversion with CE6, that is third position, that is C3 coinciding with C1 coinciding with C3, E1 coinciding with E3, and wherever B1 has moved, that is the inverted position B13. So I use again, mark this inverted position on my drawing paper, and I get the inverted position of B1, which I call B13. Now the center of the circle passing through these 3 points, B13, B3 and B33, we determine in the usual manner. We take the perpendicular bisector of these 2 lines, draw a perpendicular bisector and a perpendicular bisector of this line B1, B23. This is the perpendicular bisector of B13, B23, and these 2 perpendicular bisectors meet here, giving me the revolute pair location D3. So there is a rigid link connecting B3 and D3, and this D3 belongs to the door board, so I can have extension of the door board like this. So we have determined O2, A3, B3, D3. O4 was already chosen and C3, E3 was already chosen. This completes the design of the 6-link mechanism for the door board, namely O2, A3, B3, O4, D3 and C3, E3, corresponding to the open configuration when the door board is parallel to the roof of the garage. By driving this mechanism, I am ensured that the door board will go from C3, E3 to C2, E2 and then to the closed position C1, E1. To complete this linkage, let me now make this line continuous this line also continuous. So we get by this firm line the design of the representation of the entire mechanism. O2, A3, C3, O4, B3, A3, B3 is another link. So let me say this is link number 2, A3, B3 is link number 3, O4, B3 is link number 4, B3 D3 is link number 5, and the door board C3 E3 is link number 6. So again we have used the multi-stage synthesis procedure to design the 6-link rail-less garage door mechanism, where the garage door has the desired movement, that is horizontal movement, almost horizontal movement inside the garage, then drooping down fast to take up this vertical closed position. So we have seen how the 3-position synthesis technique for function generation, motion generation and path generation can be applied at various stages to even design more complicated mechanisms. Now we will discuss how to get 4-position synthesis. If we recapitulate the function generation, path generation, for 3-position synthesis, what we have seen that we consider the 3 inverted position of a particular revolute pair, and then the center of the circle passing through those 3 inverted positions determine the location of the other revolute pair. However, for example, for 4R linkage function generator, what we did, we chose O2 and O4, the 2 fixed hinges, O2 and O4 arbitrarily, and also chose one of the moving hinges, the crank pin at A1, and we determined B1 as the center of the circle passing through 3 inverted positions of A1, that is A1 1, which is A1, A2 1 and A3 1. We did the kinematic inversion with follower fixed at its first configuration. Then we chose A1 arbitrarily and found A21 and A31 using the principle of kinematic inversion. And B1 was obtained as the center of the circle passing through A1, A21 and A31. Now with arbitrary choice of A1, 4 inverted positions of A1, that is say A11, A21, A31 and A41, there is no guarantee that they will lie on a circle. Then I cannot determine the location, desired location of B1. Now we shall explain a technique which is known as point position reduction for such a 4-position synthesis as a function generator, which means if 3 pair of coordinated movements of the input and output links are prescribed. We are given theta 2 1 2, that is the rotation of link 2 from position 1 to 2, theta 4 1 2, that is the coordinated rotation of link 4 from position 1 to 2. One pair is theta 2 1 2, theta 4 1 2. Similarly, the other 2 pairs are theta 2 2 3 and theta 4 2 3. Another pair is theta 2 3 4 and theta 4 3 4. As is now just said that I cannot choose A1 arbitrarily anymore. So we choose O2 and O4 arbitrarily, because those are the fixed pivots. We choose them at a convenient location on the frame of the fixed link. The method that we are going to adopt is known as point position reduction, such that the 4 inverted positions of A1 become only 3 distinct locations, not 4 distinct locations. If we have 3 distinct locations for the 4 inverted positions of A1, then I can still draw a circle passing through those 3 points, and B1 can be determined as the center of the circle passing through those 3 distinct locations of 4 inverted positions of A1. We shall explain this method with the help of an example. To explain the point position reduction method, let me first recapitulate the 3-position synthesis quickly. As we have seen, these are the prescribed motion of the input link or link number 2 from position 1 to 2, theta 2 1 2, and 2 to 3, theta 2 3. Corresponding desired motion of the follower link or the output link, link number 4, is prescribed as theta 4 1 2 and theta 4 2 3. We solve this problem by choosing O2 and O4 arbitrarily. We choose them conveniently on the frame. We also chose A1 arbitrarily. Corresponding to this prescribed movement theta 2 1 2 and theta 2 2 3, A1 which goes on this circle with O2 as center and O2 A1 as radius, I can determine A2 and A3. This angle A1 O2 A2 will be theta 2 1 2, A2 O2 A3 will be theta 2 2 3. To determine B1, what we did, we considered the inverted positions of A2 and A3. We obtained the inverted position by rotating O4 A2 through an angle minus theta 4 1 2. Theta 4 1 2 was counterclockwise, so minus theta 4 1 2 is clockwise. By rotating about O4, this line O4 A2 through minus theta 4 1 2, I located A2 1. Similarly, rotating O4 A3 about O4 through an angle minus theta 4 1 3. Theta 4 1 3 is this angle which is prescribed, which is counterclockwise, so minus theta 4 1 3 is clockwise. So rotating A3, O4 A3 about O4 through minus theta 4 1 3, I located A3 1. Then the center of the circle passing through these three inverted positions of A, namely A1 which is A1 1, A2 1 and A3 1, I located B1, and the design was complete as O2 A1 B1 O4. So with such an arbitrary choice of A1, if I had one more pair of coordinated movements, say theta 2 3 4, and the corresponding movement here is say theta 4 3 4, then I could have located A4 on this circle, but the inverted position of A4 will be a fourth point A4 1, and there is no guarantee that these four inverted positions of A, namely A1 1, A2 1, A3 1 and A4 1 will lie on a circle. So for four position synthesis, I cannot choose A1 arbitrarily. How to carry out such a four position synthesis by the point position reduction technique will now be explained with the example. To explain the point position reduction technique, let us take this example of a 4-hour function generator for three pair of coordinated movements. Say theta 2 1 2 should cause theta 4 1 2, theta 2 1 3 should cause theta 4 1 3, and theta 2 1 4 should cause theta 4 1 4. We have to generate these three pairs of coordinated movements between input and output links of a 4-hour function generator. As before, we choose the fixed hinge location O2 and O4 conveniently. As we know, A1 cannot be chosen arbitrarily any longer. We choose A1 in such a way that the inverted position of A2, which we call A2 1, coincides with A1, which is same as A1 1. I will explain how to obtain this such that A21 coincides with A1. The choice of A1 is guided by this. Once after this, I can always obtain A31 and A41. So two of the inverted positions are same, so I get three distinct locations for the inverted positions of A, namely A11, A21, A31, A41. Then I can determine the center of the circle passing through these 3 points and get the location of B1. To make A21 coincides with A1, I choose A1 as follows. I draw a line at minus theta 2 1 2 by 2 with O2 O4 at O2, that is this line. This line is drawn at an angle minus theta 2 1 2 by 2 at O2 with O2 O4. At O4, I draw a line at an angle minus theta 4 1 2 by 2. This angle is minus theta 4 1 2 by 2, and this angle, as we said, is minus theta 2 1 2 by 2. These two lines intersect here, and I choose my A1 here. This is the choice of A1, which will ensure that A21 will coincide with A1. Now, once this is the choice of A1, I can determine A2 and A3 and A4 by rotating O2A by theta 212 and then theta 213 and theta 214. These are prescribed. So, I rotate O2A about O2. So, A lies on this circle, and the angle between O2A1 and O2A2 should be theta 212. Then between O2A2 and O2A3, this angle should be theta 223, which is also given, that is this angle. Then rotating it further, theta 234, which is also given. I can locate from this location of A1, A2, A3, A4. Now, to obtain the inverted position of A2, what we do? We rotate O4 A2 through minus theta 4 1 4. So, if I rotate this O4 A2 about O4 through an angle, this angle is minus theta 4 1 2. Theta 4 1 2 is given. This is theta 4 1 2, which is counterclockwise. So, I rotate it clockwise, and because of this, O4 A2 equal to O4 A1, O2 A2 is equal to O2 A1, and this becomes an isosceles triangle. O2 O4 becomes the angular bisector of both of these isosceles triangles, and because this angle is minus theta 4 1 2 by 2, this angle, so the total angle is theta 4 1 2. Thus, A21 has coincided with A11. Then we can obtain in the usual manner what is A31. I rotate O4 A3 through an angle minus theta 4 1 3. This is theta 4 1 3, which is counterclockwise. So, I rotate it clockwise because it is minus theta 4 1 3, and I get what I call A 3 1. Then rotating O4 A4 through theta 4 minus theta 4 1 4. This is counterclockwise. I rotate it clockwise and get the inverted position of A4 as A4 1. So, you see, for the 4 inverted positions, I have only 3 distinct locations. This is A31, this is A41, but A21 and A11 are coincident. By inverted position of A2, when I rotated O4 A2 through minus theta 4 1 2, I got to the same point. So, A1 is same as A21. Then the center of the circle passing through these 3 points, that is perpendicular bisector of this line and perpendicular bisector of this line. These two lines, this line and this line, they intersect at B1, and I get the required 4R linkage, namely O2 A1 B1 O4. O2 A1 and A1 B1 in this first configuration are almost coincident because of this given data. This is what we call point position reduction. Of course, we could have done this point position reduction in a different manner, such that other inverted positions, two other inverted positions may coincide. Here we have coincided A21 and A11. Let me now recapitulate what we did in this point position reduction technique for function generation with four position synthesis, that is 3 pair of coordinated movements. We chose A1 in such a way that two of the inverted positions in the example what we did, A1 and A21 coincide, and then B1 can be located at the center of the circle passing through A1, which is same as A11 and also coincident with A21 and A31 and A41. Basically, four inverted positions give rise to three distinct locations, and we can always draw a circle to these three distinct positions, and the center of the circle determines the location of the other moving hinge. It is obvious that we could have made, instead of A1 equal to A21 or same as A21, I could have chosen A1 in such a way that A1 becomes A31 or A1 becomes A41, and we get two different solutions. We have already solved with A1 same as A21, but I could have chosen A1 in such a way that A31 coincides with A1, or I could choose A1 in such a way that A41 coincides with A1. These are all inverted on the first configuration, and I will locate B1. Similarly, we can say I will convert on the second configuration and I will make A32 coincide with A2 or A42 coincides with A2, and we get two other different solutions to the same problem. So, by this point position reduction, I can have many solutions to the same problem depending on the choice of the moving hinge A, either at A1 or at A2 or at A3. Now we shall discuss this four position synthesis for a path generation problem. Previously, if you remember, we chose O2, O4 and A1 arbitrarily for three position synthesis. Of course, for four position synthesis, I cannot choose O4 arbitrarily because B1 was located at the center of the circle passing through three inverted positions of O4. Here for four position synthesis, we will get four inverted positions, and there is no guarantee that a circle can be drawn. So O4 has to be chosen in such a way that four inverted positions of O4 give three distinct locations of O4, and I can again determine B1. This I will explain with the help of an example. So O4 will be chosen so that two of its inverted positions, say O411 and O431, coincide. In the example that we shall solve, I will choose O4 in such a way that O4 also becomes O431, and of course O4 is O411 because we will invert on the first configuration. And B1 then will be located at the center of the circle passing through O4, O421 and O441. Let me now explain this with the help of an example. Let me now recapitulate the path generation problem for three position synthesis. What we did, that the coupler point C has to pass through three locations, namely C1, C2, C3. To solve this problem, we chose O2 and O4 and A1 arbitrarily. So with this choice, O2, O4, A1 arbitrarily, and C1, C2, C3 given to us. So I can locate A2 and A3 on the path of A, which is the circle passing with radius as O21 and center at O2. So I draw this circle and I can find out where is A2 and A3 because C1, C2, C3 is given to us. So C1A1 is same as C2A2 and also equal to C3A3. So from these given locations C2 and C3, I can determine A3 and A2 because AC is of given length, fixed length. To determine B1, what we did, we considered the inverted positions of O4. To obtain the inverted positions of O4, I hold the coupler fixed at its first configuration, that is A1 C1. To corresponding the second configuration, what we did, we marked A2, C2 and O4. These are the relative positions of these 3 points in the second configuration. So, if I hold the coupler fixed at its first configuration, that is A2 coincides with A1 and C2 coincides with C1, and wherever O4 goes, that I mark as O4 2 1. Similarly, I take a tracing paper, mark A3, C3 and O4. Then move this tracing paper such that A3 coincides with A1 and C3 coincides with C1, and wherever O4 goes, that I call O4 3 1. Because O4B is of fixed length, so I determine B1 as the center of the circle passing through these 3 positions, O4, which is same as O4 1 1, O4 2 1 and O4 3 1. If we add one more point on this, and I say it is C4, so now I have to design a 4R linkage such that the coupler point C passes through 4 prescribed positions, namely C1, C2, C3, C4. Then with such an arbitrary choice of A1, if I got A4, C4 from this location of C4, I could have located A4 on this circle, because C3, A3 is C4, A4, so I could have located A4. But the inverted position O4 4 4 would have been an arbitrary point, and there is no guarantee that one can draw a circle through such 4 positions of O4. So in the point position reduction, what we do, we choose O2 and A1 arbitrarily, but O4 I do not choose arbitrarily. O4 we locate in such a way that 2 of these four inverted positions coincide. I shall explain this with the help of an example. Let me now explain this 4 position synthesis for the path generation. What we say, that the coupler point of a 4R linkage has to pass through prescribed 4 positions, namely C1, C2, C3, C4. We shall apply the point position reduction technique such that 2 of the 4 inverted positions of O4, namely O4 third position inverted on the first position, should be same as O4 first position inverted on the first position, which is nothing but the choice of O4. To solve this problem, as before, I choose O2 and A1 arbitrarily. So the path of A1 I can draw with O2 as center and O2A1 as radius. It is this circle. This is the path of A, which I have marked as KA. So C1 is given to me, A1 I have chosen arbitrarily, so I know this rigid length, namely AC. So accordingly, I can find corresponding to the second configuration where is A2, because A2 has to lie on this circle and C2 is here and C2A2 length is fixed, so I can determine the location of A2. Similarly, from C3 on this circle with KA, I locate the point A3. Similarly, from C4 using the length CA, I determine the location of A4. So I get A1, A2, A3, A4 corresponding to C1, C2, C3, C4. Now O4 is chosen on the mid-normal of C1, C3 and A1, A3. This line is the perpendicular bisector of A1, A3, and this line is the perpendicular bisector of C1, C3. These two lines meet at this point and I choose my O4 here at the intersection of these two perpendicular bisectors. If I choose O4 here, O4 is nothing but O4, 1, 1. It is very easy to see that O4, 3, 1 also will be here. So I mark A3, C3 and O4. This is A3, this is C3 and this is O4. If I invert it on the first position, that is A3 coincides with A1 and C3 coincides with C1, as we see the point O4 does not move. So this is also O4, 3, 1. It is the same point O4 is O4, 3, 1. This is obvious because O4 has been located on the perpendicular bisector A1, A3 and C1, C3. So O4, A1, C1, this triangle moves as a rigid triangle from the first to the third configuration. Next we determine where is O4, 2, 1 and O4, 4, 1. To do that, we follow the same procedure of kinematic inversion. I mark C2, A2 and O4. This is C2, this is A2 and this is O4. So I make C2 coincides with C1 and A2 coincides with A1. And wherever this O4 has moved, that I call O4, 2, 1. Similarly, for the fourth configuration, I mark C4 and A4 and O4. Then make C4 coincides with C1, A4 coincides with A1, and wherever O4 goes, the O4 has moved here, and that I call O4, 4, 1. So 2 of the 4 inverted positions coincide. So 4 inverted positions give me only 3 distinct points, and I can always draw a circle through these 3 points, and the center of the circle is determined here at B1. So now I get the 4R linkage function path generator O2, A1, B1, O4 with C1 as the coupler point. Once this linkage is moved, this point C will go from C1, C2, C3 and C4. So we have got a 4 position synthesis path generation problem solved by using point position reduction technique. As I said before, with reference to function generation problem, I could have chosen different inverted positions of O4 to coincide. I could have inverted the whole thing such that O4 for the 4th position inverted on the first position coincides with O4, 1, 1. Similarly, one could have solved this by another choice, namely O4, 2, 1 coincides with O4, 1, 1 and so on. So we can get different solutions depending on which 2 inverted positions, this one or this one we want to coincide. Let me now summarize what we have learned today. Initially, we used the 3 position synthesis technique in multiple stages to achieve the design of a 6-link mechanism. Then we discussed how to do 4 position synthesis for both function generation and path generation problem with respect to a 4R link. In this 1 position reduction technique was used to achieve the 4 position synthesis, and the technique is such that 2 of the inverted positions coincide such that 4 inverted positions give us only 3 distinct locations. Then I can always draw a circle through those 3 distinct locations and determine the center of such a circle. The same technique can be used for function generation using a slider crank with 4-position synthesis. In our next class, I will take up an example to show how to use this 4-position synthesis technique in multiple stages so that we can achieve a design of a 6-link mechanism.